All right, guys, buckle up because this video might be a bumpy ride. It is implicit differentiation, and that is when we start to learn how to do the derivative or differentiate with respect to more than one variable. So this gets quite interesting. So you might have to watch a couple of these twice. That's okay. It's going to take a little time of you doing some of the examples to really solidify the understanding. So don't beat yourself up. Um, let your brain have a little bit of time to let some of this soak in and really settle. Okay, so first of all, let's find the derivative of the implicitly defined function this. Okay, that is a lot of jargon. Implicitly defined is just when you can't define it in terms of y equals. So a lot of times that means your equation is going to involve a y squared. Okay, if you actually had to solve it for y, you'd end up with a y equals something and then a y equals something else together to make this equation. But in spite of that, we can do the derivative of both sides. This is really what I'm doing. I'm taking the derivative with respect to x of both sides of this equation. You don't have to write what I'm writing at the moment, but I want to show you what's happening. This is what I'm doing, okay? Now, let's see what actually happens when I take the derivative. This is where it gets interesting. The left side's really easy. The derivative on this side with respect to x is normal. If I take the derivative of 5x with respect to this being my variable, I just get a 5. And the derivative of 1 is 0, so it's just 5. Over here, because I'm taking the derivative with respect to x, but I'm doing it using a y, I'm going to take the derivative as if it were a typical x. So I would bring this power out front, take it down by a power, but you're doing the derivative of y with respect to x. So you're going to have a dy dx attached. That's going to happen anytime that you're doing that because you're not doing the derivative of the function of the variable that you were actually saying you were taking the derivative with respect to. So I'm going to take the derivative of 3y. I'm going to treat it as if I'm taking the derivative with respect to y, which is 3, but I'm taking the derivative of y, but with respect to x. And then the last one would be, this is getting probably a little easier, negative 8x, but I did take the derivative with respect to x, so I do not have to attach a dy dx. Okay, so then if I want the derivative, though, if you'll remember, the derivative is defined as slope, so I do need to solve for this. So I'm going to take every term that does not have a dy dx attached to it to the other side, and I'm going to leave any term that does on the left. So this is going to become 8x plus 5, or 5 plus 8x, however you want to write it. Now, if I want to solve for just the slope, I'm going to factor out the dy dx. And then I'm just going to divide by that quantity. And there you have it. There's our derivative or our slope. Okay, let's try it again. Here again, I'm taking the derivative. I'm going to do, now one trick that you can do, or something you can do to sometimes make it a little easier, is you can take any term that doesn't have a y to the other side immediately. Some people do that. You don't have to. It's totally up to you. You'll get the same thing either way. But here I go. I'm going to actually do the derivative of the right. It's easier. The derivative of 1 is 0. The derivative of negative 3x squared is negative 6x. Again, because I'm doing it with respect to x, I'm good. On this side, we have something interesting happen. This is actually a product rule, guys. Don't miss that. So I have to do the product rule. Product rule is derivative of the first, which is fine. It's just negative 2 with respect to x. I don't have to attach anything. Times the second, times y. I didn't do a derivative, so just times y. Plus the first, negative 2x, times the derivative of the second. Derivative of y would be 1, but it's a dy dx. Okay, that's all of that first part. Plus, now I've got this guy. This guy would be bring the power down, 8y, but because I'm taking the derivative with respect to y, I'm attaching that slope, dy dx. Now, same thing as before. Take any non-dy dx terms to the other side. So I'm actually going to put the 2y first and then minus 6x just for style. And then I'm going to factor out my dy dx from these terms here. Negative 2x plus 8y, and then I can divide. Now, I'm going to show you a couple of things here at the end. Right. So I have a couple of things I can do if I wanted to simplify. Number one, a lot of people like to have the x terms first, and factor anything out they can. So if you notice, everybody's even. So I'm going to factor a -2 out of the top, which would make this a positive 3x. So I'm putting my x term first, and then a minus y. On the bottom, I could also factor out a -2, which would give me a positive x and a minus 4y, and then I could cancel those out. So I just want you guys to see that you can reduce these. Again, when I give you multiple choice questions, a lot of times I will have the answer in the most reduced form, so you want to make sure you can get there as well. Okay, let's find the equation or equations of the lines tangent to this. Now, none of this has changed. If I want the equation of the tan line, I need a point and I need a slope. So the first thing I'm going to do is plug in to get my point. If I want to plug in 1, this gets a little more complicated because when I plug in 1, I get, 2 times 1 squared, so 2 times 1, plus 3 times 1, but oh, I have a y attached, and then plus y squared equals 6. If I'm going to solve that, I have to do a little more work than I used to. So I end up with, let's see, I'm going to write the y squared first. This guy's 3y, and then I have plus 2 equals 6. So I'm going to go ahead and bring that 6 over. And I actually have to solve this by factoring. So this is going way back. So that means y could either be -4 or y could be 1. That's why this says equations, because the point could either have been 1, 1, or you also have the point 1, -4 on your graph. So your graph just has 2 points at x equals 1 is what this is showing. Okay, now we needed a point, or in this case points, but we also need the slope. Slope means I need derivative. So derivative means I have to do implicit differentiation. So here we go. Implicit differentiation, I'm going to take the derivative of 2x squared. I get 4x. Since I'm doing it with x, I do not have to attach that dy dx. This guy is a product rule. Derivative of the first part. So again, I'll show you how I'm splitting it up. Splitting it up like that. So the derivative of the first part is 3. Then times the second, y. Plus the first, 3x, times the derivative of y. Derivative of y is easy. Just dy dx. Plus the derivative of y squared, not too bad, 2y, but I'm attaching the dy dx, and then the derivative on the other side, the derivative of a constant, just 0. Okay, got to solve this thing for dy dx. I'm going to take these guys to the other side. So I have -4x minus 3y. I'm going to factor the dy dx's out of those two guys. I get 3x plus 2. So my slope is -4x minus 3y over 3x plus 2. So that means my slope is dependent on what both x and y are. So if I want the slope to help write these equations, I'm going to need to plug in the specific x's and y's. So I have two different scenarios. So let's try it. First, to get the first slope, I'm going to plug in 1, 1. So if I plug in 1, 1, I get -4 minus 3 over 3 plus 2. So that gives me -7/5. So this line with the point 1, 1 has a slope of -7/5. So writing your equation of your tan, can do a little bit better there. -7/5, x minus 1. Done. For the second guy, my slope is determined by the point 1, -4. So -4 times 1. I'm going to write this next part just because it's a little different. And then 3 times 1, so 3 plus 2. So this one slope ends up being -4 plus 12, or 8/5 for my slope. Okay, back to the equation. Y minus the y value. The y value here is -4, so plus 4. My slope ended up being 8/5, and then x minus 1. So again, I was plugging in the point 1, -4. That is a very complicated problem, guys. You should probably watch that part twice. All right, find the first and second derivative. All right, first derivative, I've got 2y dy dx minus 1 dy dx equals just 2. So again, factor out our dy dx. We get 2y minus 1 equals 2. So there's our first derivative. Now, when we do derivatives, we're technically, if you remember, you've seen this notation before, derivative means I take something. So if this is my equation, I really take the derivative. That's how it's really written. That's why it becomes the dy dx. So when I do the second derivative, guys, you're just taking that times this again, or you're doing that of that. That's where you get d squared y over dx. Technically, it's dx squared, but we don't use the parentheses. That's why we use the notation d squared y over dx squared to just mean second derivative. That's what that is. Okay, so I'm going to do this as a quotient rule. Quotient rule says I take the bottom, 2y minus 1, times the derivative of the top. The derivative of 2 would be 0, minus the top times the derivative of the bottom. The derivative of the bottom actually isn't bad. It's 2, but dy dx over the bottom squared. Okay. Now the top isn't terrible because that's all 0, so I basically just have this, and I get negative 4 dy dx over 2y minus 1 squared. But we can't leave this. Well, it's easier than you think. This is right here. Whoop, I'm just going to plug that in. So I'm going to have negative 4 times 2 over 2y minus 1 over 2y minus 1 squared, which becomes negative 8 over 2y minus 1. If I multiply by the reciprocal, be careful, the reciprocal is that, I end up with negative 8 over 2y minus 1 cubed. All right, and then in the last guy, we're going to start by finding the derivative. So here I go. Again, I can take this to the other side if I want. I think I'm just going to leave it. I get 2x. This is a product, careful, minus y, minus y minus x dy dx. That was me doing the product rule quickly, but I did it. Plus 2y dy dx. Again, the derivative of 3 is 0. Take everybody to the other side that doesn't have a dy dx attached. Factor out the dy dx. Negative x, 2y. I'm just going to make it 2y minus x to keep it nice, and then divide both sides by that. Now, if I wanted to make sure that those x's were listed first, I could take out a negative. So I can do that if I wanted. If I take a negative out of the top, I get positive 2x minus y. If I take a negative out of the bottom, I get x minus 2y. And that does make it a little nicer, I suppose, but there you go. For part B, I asked you to find the xy coordinates of any horizontal tangents. You got to remember this. Horizontal tangents are when the slope is 0 or the derivative is 0. So when is this fraction, which is my derivative, going to be 0? The only time a fraction is 0 is if your numerator is 0. So if I set that equal to 0 and solve for y, I get this. So what does that mean? That means that when you have x, your y coordinate has to be 2x for that relationship to work. It's a little tricky. You might have to watch that twice. For the second part, they want to know when there's a vertical tan. A vertical tan is when you have the slope has something divided by 0, which means you're looking for when the denominator is 0. So I'm going to take my denominator and set it equal to 0. X minus 2y equals 0. I'm going to solve that for y. So that means there will be a vertical tan if you have the relationship of x and then your y being x over 2. Okay, like I said, that's a lot coming at you real quick. So you might want to go back and look at some of those videos a few more times. Try some of the problems from the problem set. We'll talk about them in class for sure. We'll do some more examples together and we'll get comfortable before I test you on this. All right, good luck. Enjoy the problem sets.